Great. Hello, everyone there at home and all over the world. Welcome back to Cambridge University Astronomy. I am here today with Dr. James Trussler, who's going to tell us all about the Hubble Space Telescope and some of the amazing things that it's discovered over the last 30 years. I'm also happy to say that, fingers crossed, we actually might get to do some stargazing for the first time in 2021. So after the talk, we're going to go over to the Cambridge Astronomical Association, who are setting up the telescopes right now to look at some interesting things in the sky. But before that, we have our headline speaker, Dr. James Trussler, and he's going to tell us about the Hubble Space Telescope. So over to you, James.
Good evening, everyone, and thank you, Matt, for that introduction. So I'm so grateful to you all for joining me in tonight's celebration, because for 30 years, the Hubble Space Telescope has been surveying the heavens, and for 30 years, it has captured the hearts and minds of many. Because through its eyes, we have been able to witness the grandeur and the beauty of space in all its glory and majesty. So truly all know the name Hubble. And so today I'd like to share with you just some of Hubble's greatest discoveries. And in doing so, we will embark on a cosmic voyage, going from the confines of our solar system all the way out to the deepest depths of space, truly a journey through space and time. So our tale begins 100 years ago in the past with Edwin Hubble himself, pictured here with his trusty telescope, the 100-inch Hooker telescope. It was the world's largest telescope at the time. And Edwin Hubble, he made a remarkable discovery that truly changed our view of the cosmos forever. He found that these clouds of gas with spiral arms, they were not clouds within our Milky Way as long had been thought. They were, in fact, entirely separate, entirely distinct galaxies of their own. And so we were not alone in the universe. Our galaxy, the Milky Way, was just one of billions. Our universe was filled with galaxies. And so with this discovery, Edwin Hubble had ushered in the dawn of extragalactic astronomy and forever sealed his name in the annals of history. And so Edwin Hubble's legacy, and indeed his pursuit of the heavens, lives on today through the Hubble Space Telescope. But what makes the Hubble Space Telescope so special? Why has it given us all these fantastic discoveries? Well, to understand that, we just have to look at the name. The very nature of it is that it's in space. And to understand why that's so important, we'd have to look no further than something we've always known ever since we started looking up towards the night sky. Is that the stars twinkle, the twinkling of the stars. Twinkle, twinkle, little star is the song that we've sang since a very young age. And that is of key importance for this, because the air in the Earth's atmosphere sloshing about is constantly in motion, tossing and turning. This causes distortions, it causes turbulence. The very turbulence you might experience if you were flying in a plane also applies to this distant starlight. And so while this twinkling is great for children's songs, it's actually very poor for astronomy. If you want to see the universe in the deepest, clearest view, to space we must go. And so to space the Hubble went. On board the space shuttle, it went up into space in 1919. As we see here, it's detached, it's fully deployed, it's finally free to view the universe with its own eyes. And so the whole world was waiting in anticipation to see what Hubble would see, and none more than the team of scientists and engineers who had worked for decades on the telescope. So shown here is the NASA Mission Control, and we see the engineers cool-headed but eagerly awaiting the Hubble telescope's vision. And indeed, the NASA astronomers all eagerly awaiting, huddled around the computer to see that which Hubble would see. And so Hubble opened its eyes for the first time and gazed deep into the universe. And this is what it saw. Now, if you think that this image looks a bit blurry, don't worry. There's nothing wrong with your vision. There was something wrong with Hubble's eyes. You see, although the telescope had been carefully crafted, there was one single fatal flaw. A small part of the mirror had a small error, just 1/1000th of a millimeter. Very, very small mistake, but drastic effect on the sharpness of Hubble's vision. And so it was a disaster. Billions of dollars went into the project, and the Hubble could not see clearly. And just as if you may have blurry vision, you'd go to have your vision checked by an optician, so too did Hubble need to have its vision checked for it to be corrected. But the problem was the Hubble was out in space and it could not come down to Earth. So the solution, the opticians would have to go into space, go towards the Hubble. So here are our team of space opticians, or really, as we refer to them, the astronauts. And we see here in the lower right, the space shuttle, the way that they went up into space to fix the Hubble Space Telescope. And so here we see an image of that spectacular repair. After the space shuttle rendezvoused with the Hubble in orbit around the Earth, you see here in the lower right the iconic wing of the space shuttle, and indeed the Hubble Space Telescope itself aimed towards the Earth, which we see in all its splendor. And we see also two of the astronauts undertaking the repairs, making their way over to the telescope to correct its vision so that Hubble could see that the way that it was always supposed to. And here we see the fruits of that labor, a great recovery. Ultimately, the Hubble would be able to see the way that it was intended to see, thanks to this remarkable operation, this remarkable repair. And just to demonstrate how powerful Hubble's vision is, I like to share with you two images of Saturn, the gas giant within our solar system with its wonderful display of rings. One image taken by the Hubble Space Telescope, 1 billion kilometers away from Saturn. The second image taken by the Voyager 2 spacecraft, as it was just 100,000 kilometers away from Saturn as it ventured deep into our solar system. Now, surely it should be quite clear which image was taken by which spacecraft because of the huge difference in distance. Well, here I show you image 1 of Saturn, a very nice looking image indeed. And here I show you the second image, as well, a superb spectacle to see. So which one was made by Hubble and which one was made by Voyager 2? I think it's actually very difficult to tell. Well, it turns out the top one was taken by Hubble and the bottom by Voyager 2. And so despite the Hubble being 10,000 times further away, it saw Saturn with the same sharpness at Voyager 2. It's as if you were to take a picture of yourself, a selfie, and your friend 3 miles away in a neighboring town could take just as sharp as a picture as if you held the camera out in front of your face. Such is the power of Hubble's view. And so with Hubble, we've been able to survey the solar system in such a sharp and spectacular way. And I show here you this great gargantuan, the gas giant Jupiter. And with its incredible display of clouds, and especially the great red spot shown just beneath the center, large enough to swallow up many, many Earths at once. But for once, that's not the focus of Jupiter. No, I want you to bring your vision up towards the north pole of Jupiter, and you might see a familiar sight. It's Jupiter's northern lights. And if I play the video, you can see the spectacular display as these lights move around and shimmer as the planet itself rotates around. And just as the northern lights we have on Earth with their beautiful green glow, we also have the northern lights of Jupiter. And Hubble has been able to study these in great detail. It's caused by the charged particles circling around Jupiter and bent by its powerful magnetic field. These particles might have been released from the sun as the powerful solar wind, but also Jupiter has enormous moons. The moon of Io, with its volcanic activity, is launching all these gases out into space. These particles are getting accelerated, pushed around by Jupiter's magnetic field, giving rise to this incredible display of northern lights. And the scale is truly vast, many times larger than the Earth itself and thousands of times brighter than that on the Earth. And so with Hubble's vision, scientists have learned a lot about Jupiter's powerful magnetic field and also the composition of its atmosphere. Heading out of the solar system, we venture deep into the Milky Way, our galaxy. And I share with you here, perhaps the most iconic, the most famous picture of all has been taken by the Hubble Space Telescope. This is the pillars of creation. So, shaped by the great hand of gravity. These enormous towers stand tall 5 light years across, and in spectacular display, we see them here looming over the distant starscape. And so, driven by the ever inward pull, these great towers of hydrogen have been assembled, and within them we have stars forming in great, great numbers, by the hundreds, by the thousands. What we're witnessing here is the very creation, the birth of stars. And if we look out into the more distant scape, we have these spectacular shades of blue, green, and red. These are the gases filling the empty space, the hydrogen, the sulfur, the oxygen glowing, these beautiful bright colors as they're being energized and heated by very energetic stars that are off to our view, up to the top left. And so to get a better idea of what this starlight is doing, we can zoom in using the power of Hubble to really look at this gas cloud in enormous detail. And so while these great pillars have been carved by the hand of gravity, really shaped and sculpted by its hand, it's also being hammered away by the searing starlight from these bright blue stars that are off the image here. And just like the waves of the ocean come crashing onto the rocky cliffs, really chiseling them away, so too do these waves of light chisel away at these great pillars of hydrogen, giving rise to these very interesting shapes and forms, like these hand-like tendrils that we see, each of which is many times larger than the solar system itself, an enormous spectacle to behold. And so through Hubble's eyes, we've been able to witness creation itself, the very formation of stars. But Hubble's eyes don't just see in the visible, the light that you and I can see. Hubble's eyes can also see that which we cannot see, going beyond the blue, going beyond the red, all the way into the infrared, the light that forms the basis of your night vision cameras. And by looking through the infrared, Hubble is able to see something that you normally wouldn't be able to do, to peer through that dense gas, that dense dust that forms the foundation of these pillars. And so it's able to peer through and look at the cosmic treasures hidden within, the young stars as they're being formed, shining like jewels in the night sky. And so this is truly the power of Hubble to transform our understanding of the universe. In this particular case, how it's transformed our understanding the formation of stars and the effect that these stars can have on their surrounding environment. And as Hubble has captured the life of stars, so too has it captured the death of stars. And here I show you a beautiful starscape located within one of the Milky Way's nearest galactic neighbors, a large Magellanic Cloud, 100,000 light years away. And what you can see is this beautiful glow of red across this starscape. This is the hydrogen gas. It's been heated. It's been energized by the light from the stars that are actively forming within this beautiful field. But if we zoom further in and focus on that which we see at the center, we see a spectacular object indeed. What we're witnessing here is the effect of a cosmic explosion, a supernova. You see, when stars meet their end, when they meet their final demise, they go out in a spectacular fashion, an enormous explosion, and that is what we're witnessing here. But there's something very special about this explosion in particular. It's actually the nearest supernova, the nearest cosmic explosion that has taken place within the past 400 years. And so, looking through Hubble's eyes, we've been able to study it in great detail. And secondly, the other point that makes it so special, so the universe is so vast and the timescales for which things evolve are so long that a human lifetime is but a blink of an eye, just a fraction of a second. And so from our human perspective, the night sky, the heavens seem unchanging. They seem eternal, forever frozen in time. But in this particular case, with this particular cosmic explosion, we've been able to witness how the universe actually evolves on the timescale of years, something that we can really follow in our own lifetimes. And that's what I like to share with you now. So here I show an image of the supernova as it was in 1994. So in the center, we have the star that's been exploding, and around it, this ring of gas, this shell that's been expelled in the star's dying breaths just before it went through this explosion. And if we let the hand of time run, what we will see is that with time, the system is clearly evolving. We can witness that the central region of the supernova is expanding at great speeds, many thousands of kilometers every single second. And as it impacts the surrounding ring, it energizes it, it heats it to enormous temperatures, millions of degrees, and it glows this very, very beautiful glow, very, very bright indeed. And so through Hubble's eyes, we've been able to witness this cosmic explosion in enormous detail, and it's told astronomers very, very much about the effect that these cosmic explosions, these supernovae, have on the evolution of galaxies and the gas inside them. And so now we enter the realm of galaxies, and this was studied almost 100 years ago in great detail by Edwin Hubble himself. He recognized and he realized that the galaxy population exhibits a grand complexity. No two galaxies were the same, all were unique, truly a galaxy zoo. But underlying that complexity, also a simplicity at its heart. As Hubble found, the galaxy population could be broadly divided into two simple categories. And I show you one of these categories here. It's your typical star-forming galaxy, Messier 101, just a few 10 million light years away from us. And you see its disk-like shapes and its spectacular spiral arms laced with young blue stars, the ones that have recently formed, and these beautiful reddish pink clouds of hydrogen gas that are being heated and energized by this star light from these young blue stars. But also scattered around the view, you see these brown lanes of dust formed out of grains of carbon, grains of silicon that block the starlight behind it. And so through Hubble's eyes, we've been able to study these star-forming galaxies in all their majesty and all their glory. But following on from Edwin Hubble, he also found that there was a second population of galaxies that seems very, very different. Instead of having beautiful spiral arms and disk-like shapes and young blue stars, we have ones like this. It almost has no features at all, and it has an oval-like shape. Yellowy orange is the color that it has. And these are dead galaxies. We refer to them as passive galaxies because they're no longer actively forming stars. And through Hubble's eyes, we've been able to understand and learn a lot about why some galaxies do form stars, as we saw before, and why galaxies like this do not. And what I like about these beautiful pictures of galaxies is not just to focus on the galaxy in the center, but if we look around the view, you'll see many more galaxies to behold. And we see that these galaxies congregate, they group up, they cluster around, and this is due to the ever inward pull of gravity. And under the pull of gravity, these galaxies, they dance a dance, they dance a cosmic dance, but this dance can also be a deadly dance. What we see here is a catastrophic cosmic collision between two galaxies pulled together by gravity, smashed together, and now their stars sprinkled across the space surrounding them, and the gas and dust sprinkled around as well. And these galaxies are referred to as the antennae galaxies, and they're well named. You can see in the top right these antennae extending out to great distances caused by a spectacular collision that we're witnessing. But these cosmic collisions, these galaxy mergers, are actually very, very important within the life and death of galaxies, within their evolution. As we see here, we have this beautiful glow of blue and red, of young stars and the hydrogen gas glowing due to the collision driving that vigorous starburst activity. But we also know through Hubble that this can also lead to galaxy death, as we saw a dead galaxy just before. The power of Hubble, though, is not just that it's enabled us to get this spectacular view of individual galaxies, it's also enabled us to look at all of the galaxies within our vast universe. And so I'd like to share with you now my favorite picture taken by Hubble. It's the Hubble Ultra Deep Field, a stunning cosmic vista filled with galaxies all adrift in the grand sea of space. It's what you get if you point the Hubble Space Telescope at an empty patch of sky with no galaxies, no stars for a full 10 days. And this empty patch, what is its scale? Well, if you take the full moon on the sky and just 1/10 of that, that is what we're looking through here. So many galaxies to see, filling the image to the brim. And if we zoom in ever closer, we see that there's many more galaxies to behold. In the Hubble Ultra Deep Field alone, there's 10,000 galaxies to see. And so if you scale this up to the entirety of the night sky, this means that there's hundreds of billions of galaxies in the universe. And that is one of the most incredible discoveries Hubble has made to understand how galaxies have grown and assembled. And so in these spectacular images, not only are we probing the universe as it is right now, but also the distant cosmic past. You see, the universe is so vast that not even light itself can instantly traverse it. And so the further we look out into the distance, actually, the further we're looking back in time, as it takes longer for that light to reach us. And so as we dive deeper into the cosmic horizon, we're actually looking further and further back in time. And so looking through Hubble's eyes, we've been able to see galaxies at much earlier times in the universe's history. And indeed, if we push the Hubble to its very limits to look as deep as it possibly can, then this is what we see. We can pick up the light from galaxies like this one, the very first galaxies that formed within the history of our universe, just 400 million years after the Big Bang. We're truly witnessing the very first galaxies being formed, a split second after our universe began. And that then takes me to what Hubble has also been able to survey. It's the universe itself, really looking at things on the grandest of scales. The supernovae I showed to you earlier, these are so bright that we can see them in galaxies all the way across the deepest depths of space. And I show you an example here. It's NGC 2525, a star-forming galaxy 100 billion light years away. And if we zoom in on its lower left region, we see a spectacular bright source. This is a supernova going off, and we can actually see how the brightness of that supernova wanes with time. It has a spectacular explosion, but then it fades away. And these supernovae, they shine with the brightness of 10 billion suns. So they're truly one of the brightest beacons in the night sky, truly cosmic lighthouses standing on the shores of space. And so just like the lighthouses of old have allowed sailors at sea to scale the earthly seas, so too have these cosmic lighthouses allowed astronomers to scale the grand sea of space, the cosmos itself. And to understand how that can be done, to understand why that is the case, we go back to Edwin Hubble himself. See, not only had he demonstrated that our universe was filled with galaxies, he also realized that these galaxies were all moving away from us. The further the galaxies were from us, the more quickly they were receding. And this led Hubble to come to a startling conclusion, namely that the universe itself was expanding. What we can think of the universe as a bubble, and this bubble is growing, it's inflating, it's expanding with time, and so the galaxies and everything else inside it expand with it. And so what this means is that the distance between galaxies grows with time, and the further separated these galaxies are, the greater that separation increases, the more fast it happens, perfectly explaining the observations that Hubble had made, that the universe was expanding. And so in Hubble's time, he was able to study galaxies nearby in great detail. By measuring their motions, he was able to determine the current expansion rate of the universe, how the universe is expanding right now as we speak. But looking through the eyes of the Hubble Space Telescope, astronomers have been able to go much, much deeper, much, much further, to look at distant galaxies through the brightness of the supernovae explosions that I mentioned earlier. And so what we're probing now is not the current rate of expansion of the universe. No, what we're probing is the rate of expansion in the distant cosmic past. And so by comparing these two, the current expansion rate from nearby galaxies to the past expansion rate from distant galaxies, astronomers have been able to determine how the universe itself has evolved with time. And so what they found was truly profound, truly surprising, truly unexpected. So if we think about our universe expanding from the Big Bang as a bubble, then we might think that gravity, that great attractor, would slow that expansion down, perhaps causing the bubble to eventually start shrinking, collapsing on itself. But I'll show you now what Hubble has allowed us to see, what Hubble has allowed us to learn. On the right, I will show you the bubble of our universe and how it's expanding with time. And on the left, I'll show you a graph of what that expansion speed looks like. So let's have a look. So we have the Big Bang explosion, and the universe is expanding very, very, very quickly. But that expansion is slowing down because gravity is pulling everything together. And so it continues to slow, just as we expected it to. But then, all of a sudden, the universe starts expanding more and more quickly. It's being stretched apart, ripped apart by something. And this is one of the greatest discoveries that Hubble has made. It was truly unexpected and truly profound. Something unknown, something we don't understand, is causing the universe to split apart. And so this dramatic discovery was actually rewarded with the Nobel Prize in 2011. And with Hubble's gaze, really, it wouldn't have been possible to achieve this kind of science without it. And so we believe, because of this expansion, this dark energy, we have in fact given it a name, but to truly understand what this dark energy is, it's still a great mystery and really what we're hoping to solve in the future. So that takes me then to the future, and I'd like to focus on the future of the Hubble Space Telescope. Hubble Space Telescope is still going strong, and its instruments are working, and its vision is clear. So we hope that for the coming years, and indeed the coming decades, that it will continue to survey the night sky on our behalf. But because the Hubble Space Telescope is in space, one day its vision will begin to fail and its eyes will close for a final time. And that is when its cosmic voyage will come to a final close, and it will make its return to Earth, gliding through these Earth's atmosphere, its ashes scattered amongst the stars. But out of the ashes, a new dawn rises, and it's shining red, it's shining infrared. It's the James Webb Space Telescope. It's truly the spiritual successor to the Hubble. With its enormous mirror with 10 times the collecting area of Hubble, and being specifically designed to focus on the infrared, it's going to give us an even further, deeper and sharper view of the universe than even Hubble could achieve. And so using that new vision, what will we be able to explore? Well, we'll be able to see the beginning. We'll be able to witness the rise of the very first galaxies in the universe. Hubble has indeed been able to study these, but with the James Webb Space Telescope, we'll be able to discover many, many more. By the hundreds, by the thousands, we will find them, and we'll be able to produce a much clearer, sharper image than the one that Hubble was able to achieve there. But not just looking at the first galaxies in the universe, it'll also be used, the James Webb, to search for the origins of life in our universe as it studies the atmospheres of planets around other stars, looking, hunting for signatures of life, like oxygen, like water, in these alien worlds in the distance from our own earthly home. And so perhaps 30 years from now, I will be here again, and I'll be able to tell you all about the fascinating discoveries that the James Webb Space Telescope has made. But that is a tale for another time, because tonight we celebrate Hubble for its 30 years of discovery, forever transforming our view of the heavens. Thank you.
Wonderful, James. Thank you. That was absolutely fascinating. And I think you are not looking at the YouTube chat, but I am. You can see that people are very fascinated by everything you've been talking about. James is going to be answering a few questions now. So if you do have questions for Dr. Trussler, the speaker, please put them down there in the chat. Before we do that, I'm just going to just check in on our observers if we can and see if we can see any stars. Guys, what's the sky looking like with your telescopes?
It's okay here.
Okay, so observing is going to happen.
Yep, it's all clear here as well at the moment.
It's a miracle. This is the first time in 2021. Wonderful. Okay, so we'll give our speaker a few questions, and then we'll switch over to stargazing. We'll kick off with this question from Raj. And I think this is something you were alluding to towards the end of your talk, James, about the end of Hubble's life. So first of all, are there plans to kind of repair it and upgrade it, or are we just going to send up a new one? And when Hubble does finish, are we going to bring it back and put it in a museum, or is it going to be more kind of crashing and burning?
Yeah, so that's an excellent question. So as it stands right now, it seems that Hubble has received its final servicing mission that was actually done in 2009, with the first servicing mission being the one from 1993, repairing Hubble's vision. Of course, this could be subject to change. It is possible for astronauts in space to rendezvous with the Hubble and potentially repair it to enable it to continue to run, and perhaps even upgrade its vision ever further still than it has now. But again, this remains to be seen. It's really something that is not entirely clear. But if the Hubble is no longer being maintained, then indeed one day its components will start to fail, and it will no longer be able to survey the night sky. And because what we see here, the Hubble is actually in space, it's still actually brushing past the Earth's atmosphere. It's very, very, very tenuous. There's not much gas that it's brushing across, but steadily over time, over the years, over the decades, the Hubble's orbit will wane and it will drag it further and further closer to the Earth itself. And as it does so, it will actually re-enter the Earth's atmosphere and actually burn up. And so in that way, Hubble will come to its end. There are no plans to really outfit the Space Telescope with a parachute system or our heating system to protect it from the Earth's atmosphere. So I don't think we'll have the Hubble in a museum, but its legacy will still continue to live on in our hearts.
Wonderful. A question from Ben, age 7, who wants to know a little bit more about those first galaxies that we look at with Hubble. Can you see, have we found any more of them?
So this is actually really at the forefront of astronomy research right now, is understanding the very rise of the first galaxies in the universe. And indeed with Hubble, many, many hundreds of hours have been invested to search for these and to hunt for them. And so what we've been able to do with Hubble is so far discovered dozens of these galaxies really within a few 100 million years after the Big Bang. As we expect the James Webb Space Telescope to come along, I think it will really build upon Hubble's legacy in that regard, because the James Webb can see so much deeper than Hubble, because it has the bigger mirror, making it more sensitive to that distant light. It will greatly increase our survey of the first galaxies by hundreds, by thousands, and we'll not only be able to detect them, as we show here in this image, but really break down the light into its rainbow and truly understand the properties of these first galaxies, not just realizing that they exist.
Wonderful, thank you. We've got a question here from Mayam, who wants to know a little bit more about the James Webb Space Telescope. So can you talk about what makes it different and when we can hope it might launch?
Okay, well, so first things first, we really hope that it will launch in October this year, so October 2021. But I will say that with these space telescopes, they are also ambitious, and especially the James Webb of all ones. And so there may be further delays. It depends on how the assembly of all the different complicated instruments on board the telescope itself is coming along. So what makes the James Webb truly so special is, firstly, it's enormous. Its mirror is 6 meters across, and that's almost 3 times that of the Hubble, which was just over 2 meters. And so to be able to actually launch that into space is actually too big to fit into a rocket. And so what the mirror will have to do is it will have to be folded up into a tighter configuration so it can fit within that rocket booster. And so that is the great complexity of the design. While the telescope is out in space, it will have to unfurl. So of course the engineers have to be 100% certain that it will do so with incredible accuracy. Because as we learned from Hubble, when making the mirror, even if there's a small mistake of 1,000th of a millimeter, it ruins the view completely. And so the same problem could occur with the James Webb. And as you see here, the James Webb, its mirror is coated in gold, and that means that it's very, very effective at reflecting the infrared light, so the light beyond the red that we cannot see with our own eyes, but the James Webb will be particularly good at. And the reason why it's focusing on the infrared, which Hubble could do, but not as well as the James Webb will, is because the light from these distant galaxies, the very first galaxies in the universe, is stretched by the expansion of the universe itself, putting it from the red all the way into the infrared. And when it comes to these atmospheres of these distant planets, well,
I'm so sorry. I could see so many fantastic questions coming through. I think James would be here all evening if he tried to answer them. For now, I'm going to put this one to him. So a question from Aaron, aged 11, who wants to know, will our universe collapse at some point?
So that's an excellent question. And it was something that astronomers had actually thought could be the case for a long time, because as you rightly put forth, we have gravity, that great attractor, bringing everything together. And so if you have this expansion of the universe, as we see in this animation, yes, you have the initial expansion, it's slowing down by gravity more and more, almost screeching to a halt. And so you would have thought, okay, it's going to then reverse and start collapsing onto itself. But that's the great spectacle, the great finding that we've made recently through Hubble, is that in fact the universe is not going to that big crunch, it's actually going through this massive expansion. And so no, the universe will not come to a screeching halt in that way. It's this mysterious dark energy that we don't understand that is stopping that from happening.
Wonderful. Thanks, James, so much. I'm sure everyone at home really enjoyed that. The YouTube chat is flooded with people that found that absolutely fascinating. So we'll give you a virtual round of applause. So now I would like to switch over to our observers who, fingers crossed, are still looking at some clear skies. How's it looking, guys?
Yes, I have my first target up, A Auriga.
Good, we'll start there then. Okay, tonight we're looking mostly at the constellation of Orion, which dominates the sky towards the south. But our story starts with the constellation of the Charioteer, which is just above Orion. And we're looking at AE Auriga and the Flaming Star Nebula. Now, David's just got his images going. And what we can see is AE Auriga. That's the bright star there. And we can see that round it is some glowing gas. And this hot, massive star is just visible to the naked eye in clear, dark skies, is called a runaway star. And it's charging along at the best part of 500,000 kilometers an hour. And it's heading away from the constellation of Orion after being in a collision about 2.5 million years ago. But by good fortune, this large star of about 20 solar masses just happens to be passing past this gas cloud in the Auriga. And the cloud of dust and gas, mostly hydrogen gas, is being lit up in two ways. The first, light is being reflected from the star. And secondly, the ultraviolet light from the star is exciting the gas and making it glow. And it glows in the characteristic pinky red colour, which, can we see? It's very faint. How are your conditions over at...
You'll see the pink colour in my images in a minute.
Okay, right. We can only see the nebula very faintly.
Yeah.
Yeah, so we need clearer skies for that. So this is both a reflection nebula and an emission nebula. But astronomers have discovered in the infrared and X-ray, that's better, we can see the glowing gas around the star. Astronomers have discovered in infrared and X-rays a bow wave or shock front in front of the runaway star as it ploughs through the outer layers of this cloud. Eventually, the star will leave the gas cloud and the flaming star nebula will flame no more. Right. Thank you, David. We'll go over to...
Come to me next.
We're coming to Paul.
Yep. Let me just share my screen for you. I've got the Orion Nebula as ordered, which is a miracle given the cloudy conditions earlier. Let me just...
Yeah, it was raining earlier.
It was raining on me about 6:30. Here it comes. So this is from the 14-inch telescope with a DSLR camera on it. And what Brian has asked me to do is produce a nice short exposure so that you can see the trapezium stars. But Brian can tell you all about that. And then, Brian, when you want a longer exposure, you tell me and we'll do it.
Okie doke. Right. Well, this will be the Orion Nebula, or Messier 42, or simply M42. And it's very easily seen. And you can see the trapezium, those 4 stars in the middle, with binoculars. And that's the scene of the collision that sent that star heading towards Auriga. The trapezium was discovered by Galileo when he turned his telescope towards the sword of Orion. This was way back in February 1617. He only drew 3 stars because his telescope wasn't good enough to split the top 2 stars of the trapezium. And this was where the collision took place. 2 binary systems, each containing a couple of large blue stars, came together. And during the encounter, each pair, a star from each pair was flung away in opposite directions. One headed north and ended up in Auriga, and the other headed south and can be found in the constellation of Columba, the Dove. But that's unfortunately too close to the horizon to be seen from Cambridge. The 2 remaining stars then formed a new nebula, a new binary system, which can be found a short distance away from the Orion Nebula. But we'll look at those 2 later. But now, Paul, if you'll crank up the exposure.
Okay, doing that now. So at the moment we're on 0.3 of a second, which is quite a short exposure. Let's try 4 seconds.
Okay, so we'll just wait.
You'll have to count to 4 while the camera does its thing.
And suddenly it will burst upon us.
Sorry.
And it's these 4 stars, although it's the main bright one at the bottom that lights up the Orion Nebula.
I do have a black and white image, if that's any help.
That's all right.
Here it
comes. Don't rush it.
Keep losing it because of the clouds.
Here we come. There we go. And there you can see the Orion Nebula lit up by the trapezium. As I say, it's the bottom star that's doing most of the lighting up. And it's a bit looking, this huge molecular cloud, it's like having a bite out of the apple, and we're looking into the bite. And so we're seeing the gas lit up. And this bite is about 24 light years across. And the cavity has been blown out, as I say, mostly by that big star. And the void inside contains nearly 2,800 young stars, some of them so young that they're still surrounded by protoplanetary disks, and they're called proplyds. In 2012, it was suggested that the trapezium was also the location of a rare intermediate black hole, which is larger than a typical stellar black hole, but much, much smaller than a supermassive black hole like the one in the center of our galaxy. It's said to be about 150 solar masses. But because of it was guessed to be there because of the rapid motions of the smaller stars round the trapezium star cluster, and that the fact that there are no other big stars in the vicinity, they've been thrown out. But because the stellar wind from those stars has blown away any material, that means that no more gas or dust is falling into that black hole. So our chances of detecting it are very remote. It's going to be very difficult to find the black hole near the trapezium. And as I mentioned earlier, the ultraviolet from the light of this group of stars is exciting the gas and making it glow this lovely pinky red color.
Do you want a bit more, Brian?
Go for it.
I'm going to 10 seconds now, so that's
and then
we'll double again.
Then we'll see the...
And then I'll go to 30.
Right. While that's happening...
There you go, 10 seconds.
Brilliant. We're now starting to see the gas cloud lit up well beyond the bite, as it were. And now we are going for the 30, are we?
I'll do that now while you're talking.
Okay.
It'll suddenly appear.
What there is around in the constellation of Orion are two large molecular clouds called A and B. And cloud A, the smaller one, can be seen around the Orion Nebula area. And it's about 300 light years across. And that's better.
That's 30 seconds.
That's good. We'll leave it at that. I mean, now you can
any more will be overcooked, actually.
Yeah, you will start the sky's starting to light up a little bit, but you can see how the arm of the nebula sweeps round and covers this huge area of the Orion A molecular cloud. There's one or two other places that are lit up, but normally the molecular cloud you can't see unless it's illuminated by stars.
Brian, not to interrupt you, this is absolutely wonderful stuff. There are lots of comments coming through asking if you could give a very brief comment about what equipment you're using to get these beautiful images.
Yeah, will do.
Okay, so I'll take that one. I'm here in my home observatory relaying from just outside Cambridge, and I have a Meade 14-inch Schmidt-Cassegrain telescope, which means it's got a lens and a mirror. And then hanging on the back of it, I have a camera, which is my ordinary Canon DSLR camera, except it's been modified. It's had the infrared block filter taken out, which otherwise prevents some of this red light that we're seeing in the nebula coming through. And it's all mounted in a lovely computer-controlled setup so that I can tell it what to point at. And if I'm lucky and the technological gods are with me, it actually finds the object I've asked for. But that doesn't always happen. Anyway, back to Brian.
Okay, we'll go over to Mick in Swaffham Prior. Are you ready?
Yes, but unfortunately, that's all I've got. It keeps clouding over.
Right.
That's
Okay, shall we go back to Paul then? If you've got cloud, Paul, are you still on the Orion Nebula?
I am, yes. I can share that
Okay,
back again for you.
yeah, if you would please.
Oh, somebody else is sharing. Can they stop?
Yeah, it's me. Hang on, if I can find it.
Oh, the cloud's shifting a bit.
I
I'm
can see a bit of
struggling.
nebula from you there, Nick.
Yeah, never mind.
Yeah.
We'll go back to Paul.
What am I doing?
Right. Yeah, Paul, we're ready.
Oh, it's coming back into life now.
There you
Right.
go. What would you like me to do?
Just leave it as it is.
Okay, that's easy.
Obviously the main object is M43, which is the Great Orion Nebula. But what Mick was going to be looking at in more detail was the little object at top left, and that's Messier 43. And yet everybody overlooks it. And it's a tiddly little emission nebula. Again, only one star is lighting that area up. And it's about 2 light years across compared to the whole Orion region, which is about 40 light years across, including that 24-year bite out of the molecular cloud. But it turns out that M43 is more important than the Orion Nebula, and that was because a recent scientific paper looked at the emission of carbon monoxide in the gas you can see there, and looking at the spectral lines, you can tell if the spectral lines move towards the blue end of the spectrum, it means that bit of the gas is coming towards you. And if a spectral line is shifted towards the red, that bit of the gas is going away from you. So they measured all this area around M43 and the Orion Nebula and found that by using computer modeling, they worked out that the gas cloud is in motion, and M43 is crashing into M42, the Orion Nebula. And what's the part of the gas cloud has done is compress the gas around where M42 is, and the compressing the gas has what triggered the star formation to make M42. So without that small nebula, M43, the big Orion Nebula simply wouldn't have burst into life. It would just be this dark molecular cloud that we couldn't see. But because the gas has been compressed, star formation started, and we can see those young stars. And both these molecular clouds, A and B, are between 13 and 1400 light years away. And so what you're seeing has taken 13 to 1400 light years to reach Paul's telescope. So that's good. And now I think we're heading over to David if he's still got clear skies. David?
Hello.
Have you found the horse head?
I'm looking for it now. Oh, you must forgive my swift departure. My computer died on me.
Oh dear.
I'm just getting onto the horse head now. If you just give me a moment.
Are you able to describe your equipment while you're doing it? Can you rub your tummy and pat your head?
Yes.
Okay, while we wait for it, David will give a description of his observatory out at Halton.
I'm using two telescopes. One is a Ritchie-Chrétien telescope, which is essentially two mirrors, much like Paul's Meade telescope. And my second telescope is a refractor. So I've got a camera on each telescope that we're using at the moment. One is a color camera, which actually is not giving great pictures. And the other is a cooled black and white camera, which is hopefully going to show us something a bit better. I have an alignment problem with my of the telescope against the sky at the moment, and I am guessing a bit.
Right. Okay.
Where the horse head might be found. So.
Okay. The Horsehead Nebula, I'll just tell them about the Horsehead Nebula, is a part of the Orion B cloud. That's the upper region of, behind the upper region of the constellation of Orion, where the belt of Orion is. I hope most people know the shape of Orion. It's a large rectangle with three stars going across the middle, forming the belt. And the Horsehead Nebula is on the just beside the left-hand star of the belt of Orion, the three stars. But it's very, very faint, and it can't be seen with the naked eye unless you have a really large telescope and superb seeing conditions. Our seeing conditions aren't quite so good at the moment, but hopefully his cooled camera should be able to pick it up.
Right.
And what the Horsehead Nebula is really a finger of dark material shaped like a horse's head that's in front of the glowing gas, an emission nebula. So it's a silhouette of a horse's head. So we'll just give David a little while to...
Just see, I'm waiting for the image to form now.
Okay,
I'm just beginning to get a picture again, Brian.
Okay, so we'll go back to
Yes.
M43 when we've done with Paul's next object.
I'm still homing in on my next object. So do you want to go to Mick now? That would be a good idea.
Well, we hopefully should get David's image soon. It's on its way.
I have it.
We have it. Good.
Do you want to look?
Yeah, go for it, please.
Okay. Let's find my controls.
Because at the moment we're just looking at David.
Right. I'm trying to find how to share my screen.
That's just the inside of your observatory we can see at the moment. Yes, we can see it there. There we are, the Horsehead Nebula. And although we've run these observing sessions at the Institute, and I know we're doing it sort of remotely now, we've looked for the Horsehead Nebula many, many times during our 30-year history of observing and never seen it. But you can just see the Horsehead now. Its nose is pointing down. So it's horizontal. There's its nose. And then the back of its main is there. And that the distance between the nose and the back of its main is about 3 light years. So this obscuring material is really colossal. Many, many times, our solar system is measured in light hours, not light years. And it's found by the bright star Alnitak, which you can just see creeping into the image. And that's the left-hand star of the belt of Orion. And you can see the gas is lit up going vertically upwards behind the Horsehead Nebula. That's it. But it's not Alnitak that's lighting it up. There's a star just off screen by Alnitak called Sigma Orion. And that's the star that's lighting up the gas, and it's an emission nebula. So if we used a color camera and a much bigger telescope and a lot longer exposure, we'd see it that same glorious pinky color as the Orion Nebula.
I could try hydrogen alpha for you.
Do you want to do that? Will it take a minute?
Just take a minute.
Go for it.
Bit longer exposure.
And that will cut some of the, make the Horsehead clearer, we hope.
We'll need to wait a minute.
A minute? Oh, wait, we can wait a minute.
If we're waiting a minute, someone in the chat asked, what kind of things could you see with about a 12-inch scope? If you had a 12-inch backyard telescope, would you be able to see the kind of things that we're seeing here today?
Yes, very easily. You wouldn't see the Horsehead Nebula unless you had an exceptionally clear skies, but you get them at the top of mountain sites. But certainly the Orion Nebula and M43, the smaller one, is a grand sight in a 12-inch telescope. The only slight snag is that cameras can pick up the colours, but our eyes aren't sensitive to red. So we only see them in monochrome effectively. But even with a pair of binoculars, if you look at the sword of Orion, that will show you, you'll pick up the Orion Nebula and M43 quite happily with binoculars, and you'll be able to see the trapezium if you can hold the binoculars steady enough. Now we can see the Horsehead much clearer. That's it. Well done.
There it is.
Yeah, we can see the Horsehead shape now. And there seems a definite edge, a boundary to the emission nebula going downwards, doesn't there?
Yeah.
And again, in books, you'll see, or on the web, you look at the Horsehead, you'll see this in glorious pinky red. Okay. Right, shall we go back to Mick? Mick, are you ready? Are you still clear?
There we go. Have you got it?
Yep. And
I'm struggling with the cloud at the moment. You can see most of the detail of M42 and 3.
Right. There's M42 at the top, just where he's got his cursor. I mean, sorry, M43, the smaller one, and then the Great Orion Nebula. And then we want Iota.
Is that one?
That's it. And that's the remaining 2 stars of the collision that took place. If you remember, two pairs came together and one was flung, as each pair collided, a star from each shot off, one to the north, one to the south. And then the 2 remaining stars just moved a little way, as you can see, only a fraction of a degree from the trapezium where the collision took place. So Iota Orion is the 2 remaining young stars, and they have a very short period. They're orbiting around each other every 29 days, but in a highly eccentric orbit. They're not in a a nice uniform orbit, the collision has left them. So once when the distance between them, when they're the furthest apart, is about the same as the Earth-Sun distance. But when they get close, they're about a quarter of the Sun-Mercury distance, which is uncomfortably close for two massive young stars. And they get so close, their powerful stellar winds interact and they emit strongly in X-rays every 29 days as they get close. And the gravitational force between the two stars is so strong, it rapidly distorts their shapes, a bit like pulling on a nozzle of a balloon, and you end up with a pear-shaped balloon. That's what's happening to these two young stars. Every 29 days, as they come closer, they're turning into pear-shaped stars. And we know they didn't form together because one star is twice as old as the other. And one star just happens to be the same age as the star in Columba, the constellation of Columba, the Dove. And the other star just happens to be the same age as the AE Auriga in the constellation of the Charioteer. So that's how we've gradually worked out the what happened, and working out the speeds of the two stars in the Dove and the Charioteer, and working back. That's how we know the impact or the collision between these two young pairs happened 2.5 million years ago. Right, and that's it. Okay, we're now going to go back to Paul, and hopefully he's found his object.
I think I have. I think I'm suffering a little bit from hazy conditions now, because you can see the image is not fabulous. So I'm trying some other settings. You can see that haze over the picture, but this here is the object of interest.
Oh, right. Yes, you are suffering from, yeah. This is the Flame Nebula, not to be confused with the other.
Sorry. So this is M78.
Sorry, yeah, got you. Got you. Sorry, M78. Sorry, this is Messier 78, and you can see a little bit of nebulosity around the star, but it's not the pink coloured nebulosity, so it's not an emission nebula. This is purely starlight reflected back from the gas and dust, so it will appear slightly blue in colour. Now, you keep hearing us calling it these objects Messier or M, a number, and they're named after Charles Messier, a French astronomer who was interested in observing and finding comets. He was dubbed the Comet Ferret by King Louis XV. Messier discovered 13 comets, and in November 1758, while sweeping for the return of Halley's comet, he mistook the Crab Nebula, which we'll hopefully look at next week, for a comet. And he kept coming across fuzzy objects that could be mistaken for comets. So over the next 23 years, he compiled a list of over 100 of these objects, which we now call Messier objects or M objects. And M78, this one we're looking at, was discovered by Pierre Mouchon, and in 1780, and he was another comet hunter who had just become the director of the Paris Observatory, and he helped Messier look for these objects, and it was added to Messier's list later in 1780. And this is also part of that giant molecular cloud B in behind the constellation of Orion, and it's being lit up by two young stars. And while they're too close to be split by a telescope, with more than 50 stars can be seen there with an infrared telescope that sees through some of the dust and the gas. This is the problem. This is where the James Webb telescope will score. It's able to see through dust and gas beyond, and that's why it will produce some amazing images. So these stars that can be seen in the infrared, we can only see the two bright ones together as one star, again, are so young that they're surrounded by a cocoon of gas and dust spiraling down onto the infant stars. And the cores of these stars are just heating up. That's why you can't see them in visible light. You can only see them in infrared. But the nuclear fusion process hasn't yet started. So these 50 baby stars are halfway between a protostar and a proper star. And by a proper star, I mean a star which is fusing hydrogen into helium. Right. Shall we go back?
I've got the flame for you.
Okay, we'll have a look at the Flame Nebula. We'll just finish with that.
Okay.
So this is our last object, and it's a little way away from M78. There, we can see it, yes.
There it is.
And that's...
And here's a colour image.
Right, we can see that this is, yes, it's coming out slightly red. And again, the bright star is Alnitak, the one near the Horsehead Nebula, which is just off screen. And the Flame Nebula, as I say, is part of the Orion B molecular cloud, and it's being lit by the other star I talked about, Sigma Orion, just below Alnitak. And
it's quite tricky to balance this to bring it out.
Yeah,
the glare of the star.
We can see the flame is in sort of 3 bits. You have to get your computer screen just right. We've lost it. Is it misting over a bit your way?
Yes, I think it is.
Yeah, we've lost it to what it was. It was a bit better. It actually appeared as a sort of flame in 3 parts.
I seem to have lost it.
Yeah, it's gone.
I see the star, but the flame itself has...
Well, it's coming up for us time.
Here we are, there it is. Just see it.
Yeah, it's not as clear as it was.
No.
Well, we're coming up to time to stop, so I think that's where we'll finish. And so that's a bit better. We can start to see some of the structure of the Flame Nebula, which is an emission nebula lit up by Sigma Orionis. So, as I say, one of the objects we can look forward to next week is the Crab Nebula, the star that blew up in 1054. Okie doke. I'll hand you back to, I'll just say thank you to Mick, David and Paul out at their observatories, and hand you back to Matt.
Wonderful. Thank you all. And thank you, Brian. That was absolutely fascinating. I think lots of people really enjoying seeing how we actually do this kind of backyard astronomical imaging in real time.
It got a bit worse as we went on.
And thank you all for everyone for watching at home. Hope you've enjoyed this evening. If you have enjoyed it, consider giving us a subscribe. We do these evenings every single week during the winter. And next week, we have a talk all about what happens when two black holes collide. It should be very interesting. So wonderful. Have a good evening and see you next week.